Thank you. Thank you. Let's see. Can you hear me okay in the back? Good. It's a tremendous pleasure to be here. Thank you, Bronwyn. I've had the good luck over the years to tag along with the Neal's Yard people on many expeditions and tastings, and actually, it turns out, was walking on Jamie Montgomery's farm when I was 17 years old, before I knew anything about cheese or anything else. I have relatives who live in Wells, and we were out on an excursion. So for all kinds of reasons, it's a huge pleasure to be here. Now, I'm not going to talk about cheese. Bronwyn asked me to start with something completely different, or at least something somewhat different, which is to talk about the place that science has come to have in the world of food and cooking, as opposed to industrial food production, over the last few decades. And in fact, the reason that I started writing about the science of food and cooking back in the 1970s was that it seemed to have no place in the world of food and cooking. And it was my stumbling on the food science literature in a university library and being astonished at what I saw, and not having seen anything like it in the ordinary world of cookbooks and food magazines and so on. That's what convinced me that I wanted to write a book about the subject, and that's why I'm standing here today. So I've got a, yes, oops, from the start. So these are a couple of pictures that really convinced me that I needed to write a book about the science of cooking. I found these in 1979 in the Journal of Dairy Science, and they're micrographs of yogurt and Gouda cheese. And to me, they were just astonishing. I'd read about these things, but I'd never looked inside them in this way. And these pictures were among the first that a remarkable food scientist by the name of Miloslav Kalab was able to make of dairy products. They're scanning electron micrographs of dairy products, which are difficult to achieve, and he was a pioneer in that. So it was the fact that I didn't know anything like this in the world of the 1970s that really inspired me to do the book that I did. Now, Kalab is still around, still taking micrographs. These are now casein micelles in which you can begin to see the individual proteins inside the micelles. And he wrote this article for a glossy magazine a couple of years ago, which would have been unthinkable 30 years ago. And in fact, in this article, he talks about how difficult it was for him back in the 1970s to convince the general media that these pictures were interesting. He was very excited that he was able to show the insides of foods, and he wanted to share that with people. He wrote to Scientific American, and they wrote back and said that your photographs are going to scare our readers. And better than that, he got this response from, he worked in Canada, got this response from a Canadian television station. We would not show that there are bacteria in yogurt. If consumers stopped buying yogurt because you show bugs in it, we could be sued by yogurt manufacturers. Take your pictures. Have a nice day. So it was a very different world back then. And we've come a long way, and this conference is a remarkable illustration of that, and it's about time. But I want to make the point that it was not always thus. We kind of lost something over the centuries. So back in the 17th century, Denis Papin, who was a member of the Royal Society at the time that Isaac Newton was a member of the Royal Society, based on a growing understanding of the gas laws, invented the pressure cooker. And back then, the members of the Royal Society, mostly bachelors, would get together every once in a while, and they would have parties with the digester, as it was called back then, Monsieur Papin's pressure cooker. And some of the diarists wrote down the menus. And this particular one, which is from John Evelyn, is wonderful because it captures the the sense of excitement and wonder and thrill of experiencing familiar foods in a completely different way, because the high temperature and high pressure of the pressure cooker turned them into something completely different. So, I mean, you can see little bits there. The hardest bones of beef itself and mutton were made as soft as cheese without the addition of water or any other liquid, with less than 8 ounces of coals, so it was amazingly energy efficient, producing an incredible quantity of gravy, and for close of all, a jelly made of the bones of beef, the best for clearness and good relish and the most delicious that I've ever seen or tasted. We ate pike and other fish, bones and all, without impediment, but nothing exceeded the pigeons, and it just goes on and on and on. Tremendous excitement from the application of a scientific principle to everyday cooking. Things changed, and from that sort of excitement over the course of a couple of centuries, and it's a long and complicated story, really interesting one, but not for today, things changed and science became something else. It became a demystifier. It became something that, rather than contributing to a kind of deeper appreciation and excitement about food, made it seem much less interesting. It was now nourishment, and it was hygienic, and nothing else mattered. And if you were interested in flavor, well, it's because you had particular bacteria and you should get over it. There are remarkable recipes from these movements in the early 20th century where, for example, mayonnaise was thought to be, too variable a product. You've got eggs in there, you've got oil. You just never know what you're going to find in eggs and oil, and so there were recipes to make a mayonnaise substitute using gelatin and mineral oil instead. Medicinal more than nourishing. Anyway, then fast forward again to this modern interaction between science and cooking, which I would say is the sort of the original artisanal activity around food, an individual in a kitchen producing things with ingredients from that day for people who are going to have them right away. And that's, I think, the main avenue through which the excitement about science re-entering cooking has come over the last 20 or 30 years. And the story begins with nouvelle cuisine, and this man, Michel Bras, who was a practitioner of the nouvelle cuisine. Nouvelle cuisine was a reaction to classic French cooking, which had become kind of sclerotic. You just got the same sorts of things over and over again. It was predictable, and French chefs of a certain age became impatient with that. And they said, okay, it's time for us to think again, to be creative. We're going to reject these sauce families and the regulations that went along with them, and we're going to start to invent. And Michel Bras was famous for, and is still famous for, 2 inventions. One is the coulant down here, which is the molten chocolate cake. It's served on a plate that looks like a piece of like a chocolate cake, but you cut into it and out oozes this wonderful chocolate ganache. The other thing he's famous for, and that has been very influential in the cooking world, is that salad on the left, which he called gargouillou. He's from the Auvergne, and it's a local word, I guess, for a mixture of things. And it doesn't look that remarkable. It's vegetables and herbs and flowers on a plate with a sauce. But at the time, a salade composée in the classic French tradition would be particular vegetables and no others, and with a particular sauce and no other sauce. He decided, living out in the countryside, that what he wanted to do was do a different salad every day based on what he found walking around the Auvergne. And so he would just pick things that were edible, bring them back, combine them with ingredients from the market, and every day it would be a different combination of things. Seems kind of basic, kind of fundamental, but back then it was almost unthinkable, and it took him to think it. And the feeling that as a classically trained and ambitious chef, you could do something like that was a tremendously liberating thing for other professional chefs. So the real kick to the entrance of science into cooking in the 20th, 21st century began about 10 years after Michel Bras came up with those dishes. And at a meeting of chefs, you see lots of talks there, a French chef gave a talk in which he said something that, again, doesn't sound all that remarkable. To be creative means not copying. Seems kind of straightforward. And a lot of people at that meeting heard that, and nothing much happened. But one guy heard it and decided to take it to the extreme. He said, okay, that's really true. To be creative, you have to come up with something new, something truly new. He took as his model Michel Bras' gargouilloux, but he couldn't just pick vegetables around his restaurant and herbs and flowers and call that something new, because the idea was still Michel Bras. So he spent several years trying to figure out what could he do that would be the equivalent of Michel Bras' gargouilloux. And this is what he came up with. It's herbs and vegetables and fruits and nuts, and you look at it and you have no idea what it is you're about to put in your mouth. You only find out once it's in your mouth what it came from. So it's the idea of the gargouilloux in that it's a collection of different flavors on the plate, but this man, Ferran Adrià's idea was to transform those ingredients so that you don't recognize them, you don't have any preconceived ideas about what they're going to taste like, and so when it lands on your tongue, you're experiencing it as if for the first time. That was his innovation, and that has been tremendously influential in the world of cooking. In fact, he took that idea of innovation to the extreme, and for a good long run, until I think he became exhausted, he had the most famous restaurant in the world, and was presented, became a media figure, and was sort of the mad scientist of the kitchen. That's really the part of the rise of the celebrity chef has to do with the prominence that Ferran Adrià had for coming up with these crazy things that no one else had even conceived of as being as belonging in a high-end restaurant. He realized early on that in order to come up with novelties all the time, he needed to understand his ingredients and have input in all sorts of ways. New ingredients, new machines for processing them, an understanding of how he could combine them in different ways. And so he brought on scientists to help him. Pere Castells was the one who was responsible for many of the innovations, not only at El Bulli, but also at a couple of other Spanish restaurants as well. And these are just a couple of examples of the kinds of dishes that he was responsible for. In the upper right, those are rethought raviolis. You know how raviolis are little envelopes with something delicious inside and a nice sauce on the outside. Ferran Adrià thought, well, why don't we make them transparent so that you can see what's inside before you actually eat it, and why don't we make the envelope as delicious as the other parts of the dish, the sauce and the interior. So the envelopes here are made of veal stock. He found a way of making a film out of veal stock that was flexible so he could fold it over, and that it could take heat so you could serve it as a warm dish. And then in the bottom right, Pere Castells showed one of the restaurants how to use a vacuum distillation machine, which essentially takes ingredients and extracts their aromas, so that all you have left is a clear liquid with the concentrated aroma of whatever that ingredient is, and the rest of the food is still in the machine. So down here you have a dish that looks like, I don't know, a lemon sorbet and a champagne something or other. I mean, they're all colorless, And so you think they're going to have those sorts of light flavors, but in fact the flavors of these different elements, there are sorbets and custards and things like that. One is chocolate, one is passion fruit, one is tonka bean, coffee was another one. All things that we associate with very dark colors or very deep colors, and here they're robbed of the color, but what you get is the intense flavor. In this country, Heston Blumenthal is the leading exponent of this way of cooking, and this is one of his many inventions. It's hot and iced tea at the same time. So it's a cup of tea, and you pour it into your mouth, and on one side of your tongue it's iced tea, and on the other side of your tongue it's hot tea. And he did this by understanding and finding just the right hydrocolloid to thicken the solution just to the right amount so that he could pour two different liquids, hot and cold, into the same cup at the same time, and they had enough viscosity that they would stay separate long enough for it to be served and for you to experience it. So all of these things may give you the sense that, well, this is a lot of game playing. You know, they were just interested in novelty and not so much in deliciousness. And to some extent, that's true. They were being driven by the idea of coming up with new things that no one had ever seen before. And they began to get a bad rap for that. They also began to get cooks coming to them and saying, I want to work for you and I want to make these crazy things. And the young cooks had no idea how to make a stock or a soup. They just wanted to play with the chemicals. And so the chefs doing this kind of thing decided they had to say something about their attitude toward the use of science in the kitchen. And this is what they came up with. And what it boils down to is we're not rejecting tradition. We're trying to build on it. We think that the culinary traditions are a very important heritage, but that, as with everything in life, things progress, things evolve, and we're trying to have a part in that evolution. And even if you're not interested in innovation per se, knowing how your foods behave and what they're made of is important no matter what you're making, even if you're making the simplest, most traditional sort of preparation. And so that phase of crazy innovation kind of passed, and what's come in its place is a kind of deepening understanding of ingredients and dishes that are now just better because the chefs understand better what it is they're dealing with. This is an example of Heston Blumenthal noticing something in the kitchen, taking it to a food scientist who was receptive, and the two of them working together to demonstrate for cooks in general, cooks at large, that there was something important to know about tomatoes that people didn't know before. So Heston was one day working in the kitchen, cutting up tomatoes, and in classic French cooking, what you do is you peel the skin off, you remove the seeds, and you chop the rest of the tomato into bits and use that to make whatever you're making. So the skin and the seeds are thrown out or used in a stock or something like that. Heston noticed, just popping little bits in his mouth, that there seemed to be a lot more flavor around the seeds than in the rest of the tomato. And so he called up a food scientist friend of his. He's one of these people who had been using food scientists to help him innovate and to understand. And he said, you know, I think there's maybe more glutamate around the tomato seeds and maybe more acid because my tongue is reacting the way it does to other high glutamate foods, umami foods like Parmesan cheese. And the food scientist looked in the literature, couldn't find anything about it, so they decided to run a set of experiments based on Heston's observation and found that there's a 3- or 4-fold difference, not just a little difference, but a huge difference in the amount of flavor around the seeds of a tomato compared to the rest of the tomato, which was news to most cooks and to the food science community. Food scientists are now, after many years of just working with the food industry, realizing that there are real challenges and real opportunities for discovery in cooking in small-scale food production. And so we're now seeing papers like this one studying the making of stock. And what they found by monitoring the aroma compounds that are developed when you cook a stock, if you do it slowly for a long time, you end up with much more aroma than if you do it quickly for a short time to the same viscosity. So you end up with a sauce that's the same thickness, but depending on which temperature and time regime you pick, you end up with more or less aroma. Very useful thing for a cook to know. And then it turns out by importing controlled temperature water baths from the laboratory into the kitchen, chefs started to say, well, okay, if we're cooking eggs, for example, what happens if you cook it to 61 degrees or 62 degrees or 63 degrees? You know, before we had that kind of control, we had soft-boiled eggs and hard-boiled eggs and mullet eggs, 3 or 4 different categories. What the chefs found was that every degree makes a difference between 60 and 67 or 68 degrees. You get a different texture just with a 1 degree difference. And some of those textures are textures that cooks had never seen before because they never had that kind of control. So I think it's, 66 degrees gives you an egg yolk with a consistency that allows you to roll it out the way you would pastry dough, and then do things with it that you'd never been able to use an egg yolk for before. So within an egg, which people had been cooking for thousands of years, 5 or 6 years ago, somebody discovered that you could do something with the egg yolk simply by cooking it to a particular temperature. So I've been talking a lot about what's been going on in kitchens and in food science labs. There's also basic science, and there's been a huge change there as well. It used to be in the basic sciences that physics was king and particle physics was really the king. And everything else was not as prestigious, not as interesting, not as intellectually challenging, and so on. And that hierarchy had been there for quite a while. In 1991, the Nobel Prize was given to a Frenchman whose wife was a chef, still is a chef, who decided that that stuff was actually getting kind of boring, and the real challenge was understanding real life materials, the stuff that that we and that our foods are made of. And so he was given the Nobel Prize for studying complex forms of matter rather than simple ones. Particle physicists study hydrogen atoms and subatomic particles, trying to get things as basic and fundamental as possible. That's interesting, but so also is the complexity of the materials that you all work with and that we enjoy every day. And so he actually defined a new field, this Pierre-Gilles Degennes, which he called soft matter. This says here that it's a much better term for it than the American term complex fluids, which is ugly and discourages students from going into it. And he defines soft matter as ambiguous states of matter, the paradoxical properties of which rely on the art of mixture. And if you think about it, milk, for example, it's ambiguous because it's a liquid, but it turns into a solid without going through a phase change in the standard physical use of the word. So the materials that you all work with every day in making cheese are as complex as they get. They're as challenging, if not more so, than understanding or finding the Higgs boson. And Degennes was responsible for making it a respectable line of work to go into as a basic scientist. More and more basic scientists are going into it. There's now a journal devoted to soft matter, and this particular issue has several papers on eggs. So this is a Chinese 1,000-year-old egg, you know, the ones that are solid but translucent. And how do you get that? That's become a question of interest to physicists, which I think is good news for everybody. Harvard University now offers a course on the soft matter physics of food and cooking, and it involves guest lectures by chefs. So it's become institutionalized to that extent that cooks are now invited to give lectures at Harvard University on the soft matter physics from their perspective, and they do so alongside a physicist, and they have a dialogue. They talk about what each of them knows, practically and theoretically, and the students are having a wonderful time at it. There are, until recently, you had journals like the Journal of Dairy Science, where I found those micrographs at the very beginning, which I think were read either by other scientists or maybe by applied scientists at big food companies, but certainly not by cheesemakers. Nowadays, there are new journals coming out that are actually meant to bridge that gap, that are meant to have articles by scientists to be read and understood by practitioners, and articles by practitioners in collaboration with scientists or on their own, reporting interesting things or asking questions. These are just a couple of examples. The International Journal of Gastronomy and Food Science, which had its first issue last year, and then Flavor, which had its first issue last year. And you can see at the bottom, Flavor emphasizes work that investigates the flavor of real foods and encourages contributions not only from the academic community, but also from the growing number of chefs and other food professionals who have something to say. And more of you have something to say. So, and I think that's one of the challenges, I think, going forth from this meeting is how do we all keep in touch? How do we keep up with each other between meetings? And I think venues like this are one possibility. Another is represented by the Nordic Food Lab in Copenhagen, who simply post online the work that they're doing day after day, and they call it open source research. They're trying to share as quickly as possible, as fully as possible, the research that they're doing. And they're doing interesting things that you might find some ideas in. They currently are focusing on the use of Asian fermentations on European ingredients. So for example, making miso not with soybeans, but with buckwheat and yellow peas. There's also a Japanese mold-cured fish called katsuobushi, which is used to make dashi, the basis for most Japanese sauces and soups. And so they're making a katsuobushi-like product, mold-ripened, but not from fish, from pork, and getting very interesting results. So all kinds of interesting ideas percolating right now. And then there are just the kind of accidental, unforeseen collaborations that come out of nowhere that can be really wonderful too. There are food-loving scientists out there who just want to make a contribution however they can. And about a month ago, I got an email out of the blue from a materials science PhD who is interested in scientific illustration and in particular in animation. And he said, I came to one of your lectures at Harvard, I got your book, I've fallen in love with the subject, and I was thinking I would love to make an animation of one of the processes in your book. Would that be okay with you? And so I, of course, said, please, and suggested that he start with something relatively simple, which would be the transformation of milk into yogurt. And so what we'll show you now is the result of, it's still a first draft, but it's an example of the kind of collaboration that can happen today and the kind of, I think, power of science to help us visualize what's going on in what we do and understand it better. The little wiggly tails are the capicasein. And then the background color is changing to indicate that the liquid is being acidified. And this is not so important to yogurt making, but was still cool to see happen. So you go from a liquid into a three-dimensional gel. And that's, a guy who at the time was in Boston. He's now in China, just kind of doing it on his weekends for fun. So it's clear that there are tremendous opportunities for collaboration and for progressing in the way that the chefs have described, both in thinking up new things to do, but also understanding what you already do better and just being more in control of the cheeses that you make. Anyway, I'm looking forward to hearing all about it over the next couple of days. Thanks.